Hello, Chemistry 12. This is Mr. Chan. And what I wanted to do today was talk about something called the pH and POH scale. Now, some of you may have been already exposed to this back in grade 10 or even in your biology classes. But what I wanted to do was explore the chemical principles of what is meant by the pH scale. Now, the reason why we use the pH scale is because we're using such a wide range of numbers for the H3O plus and OH minus 1 concentrations. We need to use a scale which will make sense of the numbers, and this is called the logarithmic scale. Now, so when we use the pH scale, the P just represents negative log base 10. And the H represents the H3O plus concentration. Okay, so when we say pH, we just basically mean negative log base 10 of H3O plus. Now, another common unit we use is POH. And POH is just negative log base 10 of OH minus 1. And that's what the P stands for, negative log base 10. Now, let's say, for example, if we were to take the H3O plus concentration and we want to flip it to the pH, what we would need to do is we would just plug in the numbers, negative log whatever the concentration of H3O plus was. Now, if we were to do the other direction where we go from pH to H3O plus, then what you would need to do is 10 to the negative power of pH. So let me give you an example here. So let's say if we had a number of, let's say, 4.5 times 10 to the negative 5. And we wanted to make that into the pH. So then I would go negative log of 4.5 times 10 to the negative 5. And what you should get an answer is 4.35 as your pH value. Now, if you were to flip 4.35 as a pH and you want the H3O plus concentration, you just take 10 to the negative power of 4.35. So you can take some time right now just to play around with this on your calculators. Now, on your calculators, you should be familiar with the log button if you have a scientific a graphing calculator, okay? Or in some other calculators, you might have this button up here, okay? So what you should be able to do is play around with the numbers, play around a little bit with your calculators at this time, and are you able to flip between the concentration of H3O plus to pH and from pH back to H3O plus. So try that out for a few minutes, see if you can get it. You can pause the video, and then when you are familiar with how to flip between the two, then you can restart the video. All right. Now, when we talk about pH, one key thing is this. The number of sig figs in the H3O plus is the number of decimal places in the pH value. Recall the scientific notation. Now, back in grade 11, doesn't matter which class you were in, you were introduced to scientific notation. Let me see here. These are my notes, scientific notation. Remember scientific notation, there were two parts. There was the decimal reading between 1 and 9.999, and the exponential portion, which is the number of times the decimal moved. Now, when we translate this into pH, what happens is the last digits, in this case, notice the pH is 3 decimal places, 0.653. That corresponds to the measurement in the H3O plus concentration. That's the decimal portion. The 4 is representative of the times 10 to the negative 5. How many times the decimal moved? So in this case, 4.653 has 3 decimal places in the pH. That represents 3 sig figs in the H3O plus concentration. So again, the number of sig figs in the H3O plus is equal to the number of decimal places in the pH. This is something that you should be aware of. So I'll say look. Okay. Now, another thing with the pH scale is how it relates to the H3O plus. Because it is a negative log, pH is the negative log base 10. When you take a look at the pH scale, you will notice that there is an inverse relationship between the pH and the H3O plus. Notice, if the H3O plus concentration is very low, 10 to the negative 14, the pH value is 14. It's a very high number. Conversely, if you take a look at the H3O plus, notice a very high concentration, 10 to the 0, which is like with a molarity of 1. Notice the pH value is 0. So pH is inversely related to H3O plus. In other words, as H3O plus goes up, the pH concentration goes down. Now, 95% of all the chemicals in the world will fall between this pH value of 0 to 14. Now, some of you might say, well, Mr. Chan, can you have a solution that is a negative pH value? And the answer is yes. You could have one that has a very high concentration and dissociates completely, and you can have a negative pH value. Now, most of you are familiar with the pH scale, and you should notice is that the higher the pH number, the more basic it becomes. The lower the pH value, the more acidic it is, and the pH of 7 is generally neutral. Okay. Now, another thing that you should be aware of is if pH differs by a factor of 1, the H3O plus changes by a factor of 10. Notice in this particular case, if I go from a pH of 4 to a pH of 5, notice the value of the exponent. Notice it's a 10-time change. Okay. Now, oops, I forgot to put a 0 here. Notice if there is a value of 2 difference in the pH. Notice, let's say, for example, a pH of 4 to a pH of 6. Notice the value of the H3O plus is 100 times change. Okay. So when you change the pH by a factor of 1, it's a 10 times change. A factor of 2 would be 100 times change. Now, the other thing you should be aware of is not as commonly used is the POH scale. In this case, you're measuring the solution based on the concentration of OH minus 1. But please note the similarities. Notice as the OH concentration goes down, the POH value goes up. And as the OH concentration goes up, the POH value goes down. Notice the similarity between the pH and the POH scale. And notice as the solution has a higher concentration of OH minus 1, the POH value goes down, it becomes more basic. As the OH concentration decreases, it becomes more acidic. And again, you have a POH of 7 is neutral. Okay. And again, why do you have that inverse relationship? Is because of the fact that the P just means negative log base 10. And the negative is sort of flips that relationship inversely. Okay. Now, again, take a look. pH is inversely related to POH. Notice as the pH goes up, as it becomes from 0 to 14, the POH goes down. And pH plus POH is equal to 14, which is equal to pKw. And this is at 25 degrees Celsius. Now, I just want to show you how this is related to, some of you are familiar with this. H3O plus times OH minus 1 is equal to 1.00 times 10 to the negative 14. Now, if we took the negative log of everything, this would be pH. This, if we took the negative log, this would be POH. And if we took the negative log of this, this would be equal to 14. Now, how did they change this from a multiply to a plus? Well, it goes back to your math. Remember, when we multiply exponents, what we do is we add them together. Notice if I had 4.0 times 10 to the 2 times 2.0 times 10 to the 4, what it is I have to add the exponent 2 and the exponent 4 together to get 6. And that is why, in this particular case, the multiply becomes a plus. Now, again, remember, H3O plus times OH minus 1 is equal to 1.0 times 10 to the negative 14. Remember, that is at 25 degrees Celsius. And remember, if we change the temperature, that number will change. And this is why I highlighted here, this constant will change with a change in temperature. Okay, so this one we should also be aware of. Okay. Now, what I want to do is I just wanted to show you the pH scale. Some of you have probably seen something similar to this. And again, what I want you to do is notice, in this case, the H3O plus, notice as the H3O plus concentration is decreasing from 0 to negative 2 to negative 4 to negative 6. Notice what happens to the pH value. It actually goes up. Okay, something for you to be aware of. All right. Now, what I want to do right now is I want to go through maybe about a few examples with you, just to sort of give you some practice on how to calculate using the pH scale. All right, so let's go through a few pH examples. Now, it says calculate the pH and POH to the correct number of sig figs of a solution with an H3O plus concentration of 3.5 times 10 to the negative 5. Is this solution acidic, basic, or neutral? Now, there are a few ways to do this. So the first thing I want to do, how I approach it, is I'm going to go pH is equal to negative log of H3O plus. So in this case, if I do negative log of 3.5 times 10 to negative 5. So if I do that, negative log 3.5 e negative 5, I would get a pH value is equal to 4.46. Now, if I plug this value into pH plus POH is equal to 14. All right, I know that 4.46 plus blank is equal to 14. Figuring out the blank, this would be 9.54. Okay. And since the pH is less than 7, therefore it is acidic. Now, some of you might say, well, Mr. Chan, could I have done it like this? H3O plus times OH minus 1 is equal to KW. And then could you have solved it that way? The answer is yes. Both methods work, okay? It's whatever you feel most comfortable. All right. All right, let's give you another example here. Let's say, for example, it says a 0.62 molarity unknown acid has a pH of 2.81. Calculate the Ka. Now, the first thing is this unknown acid, is it strong or weak? Okay, that's the first question you need to ask. Now, in this particular case, there's two ways to approach this question. Number one is they ask you to calculate Ka. So when you see the term calculate Ka, this is characteristic of weak acids. Okay. Why? Because strong acids do not have Ka values. That's one hint. So this is hint number one. Okay. What's hint number two is you look at this particular number, pH of 2.81. This is hint number two. Now, how is this hint number two? Well, if you do a pH of 2.81, if you translate that, that means it has a concentration of H3O plus of 0.00155 molarity. Now, notice the significance. You might say, what's the significance of this? Notice this concentration and this concentration. Okay. So the concentration of H3O plus is less than the concentration of the acid. Therefore, it is a weak acid as well. So these are the two hints that you can take a look at. Number one, they ask you to calculate Ka. Number two is you are looking at the concentration of the acid and the concentration of the H3O plus. Now, at this point in time, this is where I wanted you to be aware that you have to understand the difference between an acid and the H3O plus. Acid is the substance that does the donation. H3O plus is the result of that donation. So in this case, what would we do? Oh, let me just get this going here. So we would go HA plus H2O is in equilibrium with H3O plus and A minus 1. And since this is weak, we set up our ice tables. Okay. And so what we have is we have our ice tables. I hope this looks familiar to you. This would be 0.62. This would be 0. This would be 0. This would be minus 0.0016 plus 0.0016 plus 0.0016. So in this case, this would be 0.0016, 0.0016. And then this would be 0.6184. Now, in this case, you have your equilibrium concentrations, and all you need to do is you need to plug in the Ka value. So, which is concentration of H3O plus, concentration of A minus 1, all over concentration of HA. So therefore, this would be 0.0016 all squared all over 0.6184. Okay. And your answer in this case would be 4.1, oopsie, times 10 to the negative 6. Now, this calculation should be very similar to your Ka worksheet calculations. Okay, so what you should have done is you should have done, question number 2A, 2B, 2C from your Ka worksheet. Remember, you had to do ice tables. So this is exactly the same thing. Okay, the only difference is instead of giving you the H3O plus concentration as a molarity, I give it to you as a pH value. All right. Now, let's take a look at this one. Example number 3. Okay, a 2.0 molarity HX minus 1 solution has a pH of 11.28. Answer the following questions. Is it a strong acid, weak base, strong base, weak acid, whatever, and justify your answer. Now, the first thing you need to recognize is this. It is a base because pH is greater than 7. Okay? Now, because it's a base, the pOH would be equal to 14 minus 11.28 would be 2.72. Therefore, concentration of OH minus 1 would be equal to, let's see, 10 to the power of negative 2.72, 0.0019 molarity. Now, notice concentration of OH minus 1 is less than the concentration of HX minus 1. Therefore, it is weak. All right. So a couple of things for you to be aware of. Number one, you recognize it's a base because the pH is greater than 7. Now, because it's a base, you want to find the OH minus 1 concentration. How is it different from this one here? Because it was an acid, pH less than 7. That's why I found the H3O plus. But in this case, since the pH is greater than 7, I had to find the OH minus 1 by finding the pOH first, and then finding the OH minus 1 concentration. And since the OH minus 1 concentration is less than the solution concentration of HX minus 1, that's why it's considered weak. Now, what do? Calculate the Kb value since it's a weak base. So Again, it's HX plus water. And since it is a base, the HX minus 1 absorbs a proton. So that's why it's H2X plus OH minus 1. And what we do is we just solve for ice tables. Okay, ice. Now, this should be very familiar now. So in this case, this would be 2.0 molarities. This would be 0, 0, minus, plus, plus. This will be 0.0019, 0.0019, 0.0019. This should start getting repetitive. And here would be 1.9971 or 81, sorry. Now, notice the setup. This looks exactly the same as what we had up here. We were looking for the equilibrium concentration, but in this case, the ice table, we set it up looking for the acid concentration of H3O plus. In here, we set it up looking for the base concentration of OH minus 1. Now we solve for KB, and hopefully you are able to solve it on your own. Okay, but the key difference here is you need to recognize that, number one, since it is a base because the pH is greater than 7, what you need to do is you need to find the OH minus 1 because that is the dominant ion in the base solution. Now, the last one is this. It says at 60 degrees Celsius, the pKw of neutral water is 13.018. Calculate the pH, POH, OH minus 1, and H3O plus. Now, a couple of key things is this. Some of you might get tripped up by saying, Mr. Chan, I thought pH was supposed to be 14. Oh, sorry. pKw was supposed to be equal to 14. Isn't that what you just said right here? pH plus POH is equal to 14. But notice it is at 25 degrees Celsius. Okay. Now, so when we look at this particular question, the first thing is we focus that this is 13.018. That's my new relationship. So in this case, I would have pH plus POH is equal to 13.018. Now, the second thing is, notice I use the word neutral water. When you have neutral water, what that means is you have concentration of H3O plus is equal to concentration of OH minus 1, or you have the pH is equal to POH. So can I rewrite this equation? Is therefore, I can rewrite the equation pH plus pH is equal to 13.018 for neutral water at 60 degrees Celsius. So therefore, pH would be 13.018 divided by 2. So that would be 6.509. And since it is neutral, therefore, POH is equal to 6.509. And then concentration of H3O plus is equal to concentration of OH minus 1, which is equal to 10 to the negative 6.509, which is equal to 3.10 times 10 to the negative 7. Now, when you look at this, again, you might say, well, Mr. Chan, I thought pH of water is supposed to be 7, of neutral water. But again, that is at 25 degrees Celsius. Since we have it at 60 degrees Celsius, that relationship value, that actual number is different. But the key word here is neutral water. For neutral water, you still have to remember, doesn't matter what the value is, you have to remember that the H3O plus is equal to OH minus 1, or the pH is equal to POH. That's what neutral means. Okay? So the one thing that can trip up people is the fact that they're obsessed with the number. They say it has to be 7, pH of 7, 1.0 times 10 to negative 7. But that is only at 25 degrees Celsius. All right, ladies and gentlemen. That is it for today's lesson. So hopefully you'll be able to attend class, and I'll be giving you some homework assignment to reinforce some of the concepts. All right, folks, thank you very much. Have a good day. Bye-bye.